I hope everybody can hear me and everybody today. And I work at the Fraunhofer IKTS, which is a research institute mainly focused on ceramics, but our division is only focused on nano-analytics. So we have like 100 people only dealing with analytics, and this is where I'm located, and this is also why I am here today to talk about the nanomechanics. And myself, I am studied mechanical engineering in the more theoretical side, and then I did my PhD in physics. So I'm a physicist and an engineer, so in between two worlds. And my topic in the PhD was also located in nanomechanics, and that's why I think I can tell you something about this world. So the topic, mechanical properties of nanoscale materials and thin films, and mainly related to nano-indentation and techniques that are related to nano-indentation. Okay. I hope everybody sees also my mouse, but we tested it. I think you do. The next hour will be somehow like this. I will give a short introduction, and then I will give pretty detailed insight into the practical and theoretical use of nano-indentation. And I make this so detailed that you can use these slides. I will also upload these slides, and you can use these slides if you want to go into nano-indentation, and you have everything you need inside here. There are also always literature citations, so you can also use these to get more detailed information, because of course I cannot show everything today. And then I will go on with some size dependencies, because we are on small scale and the materials behave differently. I will tell something about fracture toughness and further developments, new techniques. And then I will give an example where I show you that it's not so easy to get information of very thin films, but it's possible. And of course, I give you some take-home messages later on. I will start with the introduction. So nano-indentation, what is nano-indentation? In principle, it's a depth and force sensing hardness measurement. So instead of the classical hardness measurement where you just put a weight on and measuring the imprint, you're measuring the contact force and the indentation depth continuously while you're doing an indentation experiment and imprint. So this is the loading and the unloading. And you have different tips, mostly made of diamond, but can be also other materials. You have what's often used is a Berkowitz pyramid, which is a three-sided pyramid. It leaves imprints, they look like this. Of course, you can also use spheres and wedges and other shapes. So this is an imprint of a sphere, fairly big one in the world of nano-indentation, but just to image it, how it looks like. And what you can do then, you use only this force displacement curve. You don't check the imprint itself like it used to be in a traditional hardness measurement, and you determine the material parameters from this curve, and this is what I will show you in the next slides. And this is mainly hardness, but also Young's modulus and a little bit more advanced yield stress and so on. And the advantages of nano-indentation is it's relatively easy and fast. You have an easy sample preparation. As long as you have a smooth surface, everything is fine. And you indent and probe very small specimen volumes. And then you can have really local information of the mechanical behavior of your sample. And for example, you can use this for mappings. So you see all the small dots here are single experiments like these. And then you can have a map of the mechanical properties of your microstructure of a polycrystalline metal or whatever you have. And in this case, it's a hardness map. You can see that there's a hardness increase at the grain boundaries, and yeah. So this is like the main thing why you use nano-indentation. There are different tools available on the market. I of course cannot show every tool, And they also have different working principles. I use mainly two tools, two XC2 tools. This is one is the Heisitron Tribo-Indendo 950 tool, which where the displacement is measured using a capacitive displacement a double plate capacitor, and we have two different transducers for this. One is the standard transducer, which has already a high resolution, and then we also have a MEMS device, which is very, very fragile, called X-probe, but it has an extremely high resolution, close to AFM resolution. And then there's also a tool I use, it's called ASMEC UNAT, and this has an inductive displacement measuring unit and has a little bit lower resolution, but it's more robust, and it has also a lot of advantages. So, and there are numerous other tools on the market. Don't want to go in detail too much. And I want to go right straight to the elastic plastic nano-indentation, which is the most commonly used. And I start with this experiment in bulk materials. So these are the experiments you've seen before, just an imprint, and this is an AFM scan of such a Berkowitz tip, and this is a sketch, a drawing of the Berkowitz tip. And when you have this force displacement curve, with these sharp tips, with a pointed tip, you always get immediately plastic flow because they are very sharp, and you always have plastic flow in the material. And so the main method used to analyze the data is the so-called Oliver-Farr method, and I also uploaded this paper on the online drive, so you can take it immediately from there. So this is one of the main papers in nano-indentation. If you deal with nano-indentation, you have to read this one. And there's also a standard on this. I'm not so sure how in Portugal you have access to the standards. So this is the standard name, but I guess you also have access to this. And yeah, and with the solutions I show in the next slides, you can then determine the hardness and the elastic modulus. And yeah, just a hint, if I have literature, I always cite them in the lower part of the slides. So how is the principle of the analysis of these nano-indentation data? So in principle you use Snedden's solution for force displacement curves, and this comes out to a formula like this. And using this formula, here you have the force displacement curve again, you fit the unloading curve because you assume the unloading is fully elastic. So you load and there's plasticity, and you unload and it's fully elastic. And everything inside here, this hysteresis, is the plastic work. And once you've fitted this unloading curve with this formula, you are able to get the unloading stiffness at maximum force. And with this unloading stiffness, you can then calculate the contact depth. The contact depth, this is the indenter tip in contact, and this is after the loading, this is the residual imprint. And in contact at maximum force, you have a depth where the indenter tip is really in contact with the half space, with the specimen. And then the rest is elastic deformation. And using this Snedden's theory, you then can get the contact depth. And from this contact depth, yeah, you have the contact depth, and then you can determine via the area function, so-called area function, which is a function of the contact area, AC, over the contact depth. You can then calculate the contact area, which is the area exactly here, which is then also the area of the imprint. And if you then have this area and the contact depth, you can determine first the hardness, because hardness is only maximum contact force over contact area. So you directly derive the hardness. And one step further, mostly you're not interested in hardness, because hardness, it's not a physical parameter, it's just an engineering parameter which you can compare materials, and but it's not a physical parameter. You're more interested, for example, in Young's modulus, which is a real elastic constant of the material. And this you can achieve by this Bolychev solution. And for this you use the unloading stiffness you determined one step before. And this depends on the contact area again, which we also have. And this is then the reduced modulus, which contains elasticity of the sample, what we want to have, and elasticity of the tip, which we have because we mostly use diamond tips where we know the elastic constants. So using this solution, we then get the Young's modulus of the sample, which is down here. And this is the standard treatment, and this is already pretty good. And you're good to go for first try, but if you really want to have extremely detailed data, there are some correction. The standard method has some inaccuracies, and some of them you can correct, and then you get this indentation modulus that you determine with the standard. You can get closer to the real Young's modulus, and these corrections and the necessary calibrations I will show you in the next slides. First of all, we have this epsilon factor, which is in this Snedon solution, and this is used in a standard treatment as a constant, but in reality it depends on the actual shape of the tip, and you can calculate this more detail using this formula. Everything I tell you now is in this paper from Kotopa and Janet, which is down here. So if you correct this, you get a little bit closer to the real Young's modulus. And there's also a correction of the radial displacement, because for very elastic dominated materials, you get a lateral movement of the material. And the standard treatment assumes that the contact area under full load and after the loading is the same. So this contact radius is the same. But for very elastic materials like glasses, this is not true. And then you can correct the contact area due to the lateral displacement. And so this can cause errors up to 5% for glasses like fused silica. So, and you also can correct this pretty easily. One of the things, if you indent in very plastic materials like soft metals and so on, you get the so-called pile-up. This means this is a cross-section of an AFM scan of this indent, and if the material is really plastically flowing, there will be material squeezed up on the side of the indenter tip. So this is the normal plane, and this is material plastically flowing upwards on above the normal, the original surface level. And of course, you have additional contact area here, which changes the hardness and the elastic modulus. So there's you can correct for this in the easiest way if you're doing a pre-AFM scan and measure the additional areas here. So this triangle here is the area the standard treatment assumes, and the dotted dashed line is the real contact area, and then you have this additional area here. And you can calculate a so-called pile-up correction factor, which actually is factor which is the ratio from the real area that we have in contact to the area the standard treatment produces, so the triangle. And you correct everything, and then you can get a more correct contact area, and with this a more correct hardness and a more correct Young's modulus. Everything, if you want to go step by step, everything is here. And this is just to show you that it's pretty important. These are some results and with pile-up correction. On the right side is simulation results, finite element simulations of indents in materials, and here is experimental data on the right. So we see here on the x-axis E over y, E is Young's modulus and y is the yield stress, and this is a rough factor for the elasticity and plasticity of materials, so very low numbers is very elastic dominated materials like glasses and so on, and very high numbers are materials with very plastic flow, so soft metals. And here you have the ratio from the indentation modulus we determine using the data treatment to the input value. So 1 would be perfect. So if it's 1, the modulus is perfectly determined. You see for low E or Y values, it's pretty good with the standard treatment because there's no pileup, and as soon as you go higher, there will be pileup, and there will be errors up to 20% for the Young's modulus. And then if you use this pileup correction, you stay really flat at 1, so at the perfect value. And the same, of course, with much more scattering is true for experimental data. So we have a deviation here. The open symbols are without correction, and then the red filled symbols with correction, and you get much closer to the real modulus. So if you have really soft materials, you have to check for pileup. For hard, elastic materials, it's not so important. But it's always good to check the shape of the indents you produce and not use the force displacement completely blind. This is the message here. And one of the most important things in nano-indentation is calibration. Calibration of the machine and calibration of the tip itself. And if you don't do it right, then you can really get errors up to 100%, so completely meaningless measurements. And sometimes calibration takes longer than the actual measurement. But it's very important. The reason is because these tips in this small scale are never perfect. They have a tip rounding in a tip, maybe the angles are not perfect. So you have to calibrate the real shape. And also the machine stiffness mostly is not a constant. Sometimes you can assume that it's a constant, but still anyhow you have also to determine this constant. And the errors are shown here. So this is a very new, the blue is a very new tip, and so the shape should be pretty good. And so this is contact depth, and you see the blue line for the Young's modulus is pretty straight, so pretty good. And then if you wear the tip and use the one tip to measure after several times again in the same material, then you have a tip rounding, and depending on the age, at lower contact depth, the data you get are for the Young's modulus are completely wrong. They are overestimated up to 100%. And the reason for this is that due to the tip rounding, the shape of the tip changes, and if you use the shape of the unchanged Berkowitz tip, in this case it's a Berkowitz tip, then you make really big errors. So after a few experiments, you always have to calibrate the area function new. Otherwise you get really big errors. And how do you do this? You use the standard treatment, but in an inverse way. So you take materials where you know the Young's modulus, and most commonly used is fused quartz, fused silica for this, and you make indents in it, and then you use the Oliver-Farr method reversely to then get the area function on contact, so the function of the contact area over contact depth. And if you use only one reference material, let's say fused silica, and you can use indents at bigger indentation depths where you assume the shape of the tip is still good. You can get a constant value for the machine stiffness, or you use two reference materials like fused silica and sapphire, and then you get two area functions, but you determine this area function with one tip, so the difference between these two area functions can only come from a non-correct stiffness function. And so if you then fit this both area function together, you can get the stiffness function of the material. There's one thing I have to say. If you silica, what's most commonly used is a glass, and a very anomal glass, so it strongly densifies during indentation. So there can be small errors at very low indentation depths if you calibrate with silica. You have to take this into account. If you really go for very, very low indentation depths, it's maybe better to calibrate with sapphire or other glasses like this BK7. And this is then finally how such a area function looks like. So this is contact area over contact depth, and if it would be ideal, it would be the dotted line here, and this is the real area function. So it's not perfect, but once you have this calibration function, you can use it, and everything is perfectly fine. So this was everything for bulk materials, but in thin films, which is a very common situation in nano-indentation, there's something you have to take care of. Because everything I showed you now, the standard analysis is only valid for half spaces, and which means bulk materials. And so the problem is, so this is the thin film and this is the substrate, and in thin films you always have to divide between hardness measurement and Young's modulus measurements. These are very different tasks in nano-indentation. Because the hardness, it's mainly determined by the plastic flow, and so mainly determined by the yield zone, which is red in this case. So these are FE simulation results, and the deeper you indent, the bigger of course the yield zone gets. And as long as the yield zone is within the thin film, you more or less get the hardness of the thin film without influence of the substrate. And only if the yield zone touches the interface, then you get a mixture of behavior of the substrate and the thin film. And but completely different to the elastic modulus. The elastic modulus you measure with nano-indentation is mainly determined from the elastic field outside. So everything that is outside the red yield zone here. So and this elastic field outreaches much further than the yield zone. So you almost always get influence from the substrate in the measurement of the Young's modulus in thin films. And of course, these measurements on thin films behave differently if there's a stiff substrate on a compliant film or compliant substrate on a stiff film and so on. And even multi-layer films. So you have here, I will show you some points that you have to take care of in the next slides. For hardness measurements on thin films, there's a safe rule. That means, it's called the Büchler rule. That means if you only indent 10% or lower of the film thickness, contact depth, you are safe to get the hardness of the thin film and not substrate influence. And the reason for this is, I did some FE simulation, so this is the indent, and you have the yield zone here, the yield zone ends here, and this is the radius of the yield zone, and this is the contact depth. And I calculated the ratio of the yield zone size depth to the contact depth. So this is this axis, and here again E over Y, so for a variety of different materials and also different hardening exponents. And doesn't matter what material you use, it's mainly this ratio is well below 10. So it doesn't matter which material you have, the yield zone is always a maximum 6-7 times the film thickness. So this 10% rule indeed is valid and a safe rule for hardness. And but there's another thing in hardness. Hardness is a measurement of the plastic behavior, and for this you have to have fully developed yield zones. And if you have a rounded tip or even a spherical indenter tip, in the very low indentation depth the yield zone is not completely developed, and then you don't get a hardness, you only get average contact pressure. And so you have to have pretty sharp tips to measure on very thin films. And what happens if it's not sharp enough? You see here hardness values determined with nano-indentation over indentation depth, and so for different measurements. So, and here this is the substrate and this is the film, and you see that you're coming from indentation depths where you're already in the substrate, and then you go into the film, and then the measurements tend towards the hardness of the film. So at 10% you would assume that you get the hardness of the film, so somewhere here. But then you suddenly have a drop here, and this drop is not due to a hardness drop in the film, because you tend here from the substrate to the film properties. This is due to the tip rounding. So you're not able to reach completely the 10% because the tip rounding is too big. And there's also a safe rule. This means you are able to measure the film hardness if you have a tip radius, which you can determine from the area function calibration. This is 1.5 to 2 times or smaller than the film thickness. So then this drop will happen at so low indentation depths that you really can reach the 10% of indentation depth of the film thickness. So this is the second rule for hardness. So now 10%, you say, okay, nice, and I also want the Young's modulus, and I use 10% indentation depth of the film thickness, and then I also use these measurements to determine the Young's modulus of film, and this is not appropriate. It doesn't work because the elastic field outreaches so much further. You can see this here for 2 different film systems, and the red line here is 10% film thickness, and you see, and this is the reference value of the film modulus, and you see at 10% you're far away from the real modulus. Is still full of substrate influence here, so the substrate on this measurement is somewhere here, and the substrate is somewhere here, and you still have substrate influence. And you have to go really to low indentation depths, let's say 1% and below, to really get the modulus of the film, and often this is not possible because the resolution of the tool is not high enough. So this is really a problem. The substrate influence in thin film measurements and nano-indentation is really a problem. But there's also something on the good side. There's no problem with tip rounding because we want to have elastic measurements, and the theory behind is elastic contact. So we can also use the theory for completely elastic measurements. There's no need for a developed yield zone, so no problem with tip rounding, only problem with indentation depth. So you can go 2 ways. Either you go for very low indentation depth if your tool can make it and if the film is thick enough, but there's also another way. You can use the elastic unloading curve and then use an analytical solution called effectively shaped indenter. And there you take the unloading curve, which is assumed to be purely elastic, from the original indenter shape on the deformed substrate, and you fit an indenter shape on the unloading curve that produces the same unloading loading curve, but on a fully elastic half space with an undeformed surface. So this gap and this gap is the same, and this is a fully mathematical construct now, which represents the elastic part of the unloading. And for this mathematical construct exists a complete force displacement solution of layered half spaces and a full stress strain solution. So then you can use this and correct for the substrate influence and get substrate free values also for this elastic plastic indents. And here a short proof that it works. So we have seen before that for normal data treatment you need, let's say, 1% of indentation depth to film thickness to get values for the elastic modulus of the thin film. And here we have the same ratio, and you can see with using the effectively shaped indenter you can get for this compliant film on a soft substrate. You can get information on the thin film modulus already from 12%, 15% on, and for compliant film on a stiff substrate like here, you can get even until like 50%. You can get good information, so pretty good. So with this solution you're also able to get information on very thin films. I will skip this. I left it in the slides because you will get the slides. Because this is a very special. If you have to indent at edges or vertical interfaces, there's a way in using the structural stiffness to correct the measurements close to these edges. But this is a very special case. If you need it, you have all the information here. But for today, due to time reasons, I will skip this and continue. And so the next step, so everything we had now was elastic plastic nano-indentation, so you have plasticity there. But you can also go for fully elastic nano-indentation. And in bulk materials, you can just use the Hertzian contact theory, which was developed at I think 1881 or so really old, but still valid, and it will be valid for the next 3,000 years. And so when you have a Hertzian elastic contact in a nano-indentation, mainly if you of course use spherical tips and you have elastic material, or at very low loads, also the tip rounding act as a round spherical contact. So either you use real spherical tips, or for low indentations with rounded tips you also get Hertzian contacts. The only downside of Hertzian contact theory is that it's more demanding on surface roughness, so you have to have very flat specimens, and of course if you have a very soft metal it's pretty tough to get elastic contact because there will be always plasticity. But if you have elastic contact and you determine the Young's modulus of Hertzian contact, it's normally more accurate than from the standard Oliver Farr method for the other data treatment, which of course you can also use for elastic contacts here. So this is the Hertzian contact, so this is the measurement for very low loads, and the red line is the fit of the Hertzian load unloading load force displacement curve, and this is the contact theory and the contact itself. So if you have an elastic contact, you have no hysteresis, so loading and unloading will be on one curve. This is a good hint if you have elastic contact. If there's some hysteresis, you don't have elastic contact. You also have to calibrate the shear radius because the shear radius is normally not a constant over contact depth. So here you have contact depth and shear radius, and you also have to calibrate the machine stiffness. But this we've seen already before, and you also use this. You also do the calibration in using an inverse usage of the Hertzian formulas, like we did with the Oliver Farr formulas for the elastic plastic contact. And if you've done this, then you can see here the red dots are the Hertzian contact. So these are experiments, elastic experiments, and the data analysis is for the red dots done with the Hertzian contact, for the black dots done with the Oliver Farr method. And you see with the Hertzian contact you get less scattering and better results for the elastic modulus, where for the Oliver Farr method you have a bigger scattering. So it's more accurate than the Oliver Farr method. And in thin films, Hertzian contact is only for bulk materials, so for half spaces. And in thin films you can also, there's a theory called image load method, and this is a full analytical solution for a spherical Hertzian contact of a layered half space, so a thin film system. And you get the full force displacement solution, of course, and the full stress strain solution. And with this image load method you can then fit elastic contacts of thin film systems and then correct the data from the substrate and get purely the thin film moduli. And with this, you're able to really study extremely thin films, like shown here. You can get the modulus of single-digit nanometer thin films. So it's a pretty powerful tool and solution. Yeah, this was a pretty big block on the nano-indentation itself, and so you have all the tools if you want to do nano-indentation and analyze the data. I want to tell you something about size dependencies, because nano-indentation we go for very small indentation and experiment sizes, and there's something changing in the small scales. In normal macroscopic testing in conventional plasticity, you always assume, so we are now for hardness measurement, in the field of hardness measurement, you assume there's an infinite amount of dislocations in the material. So if every plastic deformation can use the dislocations present in the material. In small scales, this is not true anymore. So normally, what is called a size effect or indentation size effect is everything that deviates from the conventional plasticity, which would assume that doesn't matter how big the experiment is, the hardness is always the same. Normally what you see, it's an increase in hardness. So this is the macroscopic hardness, and if you go to small scale, you get an increase in hardness. There's also reverse indentation size effect, but this is not very common. Normally you see this increase here. And there are numerous models to explain these indentation size effects. One of the more popular is the nano-scale model that says in small scales you need geometrically necessary dislocations, called GNDs, to enable the huge strain gradients, because the smaller you get, the bigger the strain gradients get. So you get extra dislocations to get the big strain gradients, and then you have extra dislocations that can block each other, and then you get a hardening. But there are numerous other models and also numerous other size effects. But I have to say a big but. Very often, size effects are only effects come from surface film, like oxide films. The polishing influence, if you do mechanical polishing, you get dislocations from the polishing in the surface, or wrong calibration. We have seen this increase. I showed you in slide 14, where if you have a wrong calibration function, you can also get an increase, or other effects. I put one paper which shows another effect which can look like an indentation size effect. So if you find something like this or like this, you really have to check very carefully your calibration, your sample preparation, if this is a real size effect or if it comes from something else. It's very common that size effects are not real size effects, but come from the measurement. For hardness, size effects are very common, but there are also reported size dependency on Young's modulus, even if it's not so not so common. And there's one report that for copper indents, you have with bigger indentations in single crystal copper, you get the mixed elastic modulus. For bigger indentation depths, and you go for small indentation depths, it splits up to the directional Young's moduli. And also there are some hints that on lead and so on, you get an increase in the Young's modulus. So not my measurements, these are reports from literature. I would check them carefully if it has nothing to do with the calibration and so on. Just to say that in nano-indentation you always have to check for size effects, because materials behave differently in small scales. I will also tell something about interfacial fracture toughness, which is pretty important in material testing. So this is a microelectronic device with a catastrophic crack that travels along the interfaces. And if you have a brittle material, then you can use the Griffith crack theory, which is just a strain release, and you create new surfaces, and the energy of the surface created then controls the crack growth. And you have different modes. Mode 1, just the opening. Mode 2, shear molding, and mode 3 would be torsion. And yeah, you can then, if it's a brittle material, you can pretty easily determine the fracture toughness. And there are several ways that we calculate or measure the fracture toughness for 4-point bending. So you have the pre-crack here, and the crack travels in both directions at the interface that you prepared here. Or double cantilever beam, you follow the crack with the camera in this double cantilever geometry, and you can determine the fracture toughness at different positions. Or something also we developed is wedge indentation. You have the thin film, you press the wedge inside, and you measure the crack. I will go in detail a little bit later. So here a comparison of the 4-point bend and the wedge indentation. 4-point bend is a standard method. It's pretty reliable. The values for the GZ you get pretty good, and but you have this complicated sample preparation. So you have to have these 2 bars and a pre-notch and so on. And the wedge indentation, it's still under research, but the results are pretty good so far. And you have almost no sample preparation. As long as you have the film on a substrate, you can go. And it's done in a nano-indentation device. You just put a wedge tip there. And it's also local. It's much more local than this. So you can have 6 microns wedge, and then you can have a very local measurement of your fracture toughness. This is how it's done. You press the wedge in the surface, and the deeper you put the wedge in the surface, then you get an interfacial crack, and then you measure the surface of the crack, and from this you can get then from the removed volume in the indentation you get the GC. This is the fracture toughness. This is how we do. We do it with automated image correlation. We determine the crack size, and then we determine the fracture toughness. And this is a comparison between 4-point bend and wedge indentation results, which are pretty promising. So they are almost identical. This was fracture toughness, which is an important point in micro and nanomechanics. And I want to show a few slides on further developments. One thing is that a lot of tools these days go in situ inside other tools, especially microscopes or multiphysical characterization devices. So for example, in scanning electron microscopes, you have this miniaturized nano-indentation and mechanical testing platforms you can put inside the microscope. You have mechanical, electrical testing possibilities with the tool, and you have focused ion beam, so you can produce small experimental geometries, EDX for chemical composition determination, or EBSD for crystallographic determination. So you can really have multi-physical characterization with the combination of these tools. The same for transmission electron microscopy. You can also get this mechanical testing platforms inside the TEM, and you get really high resolution data from the imaging of the sample and chemical composition in combination with mechanical, electrical, and heating. And you can also go inside an X-ray microscope, of course, and also the same combination. Some examples here inside the SEM, so you can really see what happens. So this is a pillar compression, and you compress the pillar, and you can see the slip lines, or you can look directly at the indentation with the diamond tip. In situ in the TM, you can really look in very small scales inside the materials. So you can see here's also a lot of dislocation. So when you compress this pillar, the dislocation disappears, the dislocation starvation. As you can do everything inside the microscopes. And so this is inside the X-ray microscope. And if you're not inside, you can only see the surface. So this is an indent in carbon fiber enhanced aluminum. But if you have the X-ray microscope, normally this is a video, but this is a PDF, I cannot show the video. So here you have the tip and the material, and you can really see inside the material how the tip is going inside the material, and later on you can do a 3D reconstruction of the crack produced by this indent. You can also overlay the contact tip with a vibration, so modulus mapping or dynamic mechanical analysis. You can either use it during indentation to get a stiffness depth profile, or you can use it in the scanning mode. You have the tip in contact mode, like an AFM in contact mode. You have a vibration and you measure the amplitude and phase shift, and from this you can get the complex modulus, so the storage modulus and the loss modulus. So this, where the loss modulus is the viscoelastic response, you can get damping. So you can get a mapping, for example, of this multi-phase polymer, and you get areas where there's more damping. And of course, you can also extend the data analysis for different parameters. For example, one important parameter of material is yield stress. You can get yield stress from indentations from expanding cavity models. I put the paper here, or from loading partial unloading, which I also put the paper here, or representative strains, neural networks. You can also get elastic constant beyond Young's modulus, like Poisson's ratio for multidimensional nano-indentation experiment. And also one new direction is to go for very fast indentations, or only split-second indentations to get really huge mappings. So these are the main directions nano-indentation is going these days, or nanomechanical testing in general. Before I conclude, I want to give you one example how we use nano-indentation, and this is a characterization of ultra-low K films. I will say what ultra-low K films are. Ultra-low K films are mainly these days organosilicate glass films, so complex materials. So it's glasses with organic content and porosity. So we have a glass, an organic material, and porosity in one film. Sorry. And so these are the sample building blocks. You have silicon and carbon bonds and hydrogen bonds. There are two ways to prepare these materials, one from a liquid phase and a spin-on, and then you bake it, or you use chemical vapor deposition. So you have the precursor, you crack the precursor on the substrate using temperature or plasma, and then the organosilicate gas is left on the substrate. You use these materials mainly as isolators material in microelectronics, which is the example I will show you. But you can also use it for filtration, biomedical application, catalyst supports, hydrogen storage, and so on. This is how it looks like in a microelectronics. So these structures are copper connecting lines, and the layers in between are these ultra-low K materials. Why the organosilicate gas is called ultra-low K? Because you need very good isolators in between these conducting lines. And the smaller the microchips get, the better the isolators have to be. And the dielectric permittivity, normally called kappa in microelectronics, is called K. So K has to be very low to have a good isolator. And these are and then you have these ultra-low K materials. This is why they call ultra-low Ks. And organosilicate glass without porosity have a K value of roughly 3. And if you want to get better in terms of isolation behavior, you have to lower the K value, and this you do with introducing porosity up to 50%. Over 50% the materials get unstable, but then it's very nice linear behavior. The more porosity, the better the isolation behavior. But on the same side, in the same manner, the modulus, Young's modulus decrease also linearly. It's almost the same behavior. And the problem is, if you have a very low modulus, the fracture resistance also decreases. So if you use these materials, it's very likely to get catastrophic cracks in your microelectronic structure. So to optimize these materials, so what you want to have is high modulus and low K value. You have to measure these materials, and this is pretty challenging for these very thin, porous organosilicate films. The problem is this: we have already seen that we need to have the elastic field inside the thin films, otherwise we measure the substrate. And we use two different tip geometries, the cube corner tip and the backward tip that you already know. And we checked the elastic field with finite element simulations. So this is all, both images are the elastic field for these two different tips at the same indentation depth. So this is much sharper tip, the cube corner tip, compared to the Berkowitz tip. And the border to the yellow color here is 2% elastic strain. So this is like a representation of the elastic field. And you see the elastic field for the cube corner tips is much, much smaller than for the Berkowitz tip. So you would say, okay, the cube corner tip is much better for thin film testing, so we used the cube corner tip. Of course we did so, but we also compared it to the Berkowitz results. So this is Berkowitz and this is cube corner tip, and this is contact depth over film thickness, so 10%, 1%, 10%, 1%. And the Young's modulus for different porosities here. The color code is for the porosity. And you really see this is our standard transducer, already pretty high resolution, that at the limit of our standard transducer there's still no stable value. So there's still substrate influence here. So you really need for this very high resolution fragile MEMS device, this X-probe I showed you in the beginning, to reach the stable state here where you can get the Young's modulus of the thin film, because the elastic modulus of the elastic field of the Berkowitz chip is so big. Much better for the cube corner. You see that it's flat from much higher indentation depth on. So here already at 10–13% it's already a flat, and you can get the modulus of the film. So you would say, oh, just use the cube corner tips. You don't need the extra effort here. But we are testing on porous thin films, and yes, it's a big difference. It's different because on porous thin films the stresses and hydrostatic stresses around the tip are really high, so you get densification around the tip. And this is the gray area here. This is the areas where you get densification. And for the cube corner tip with this very small concentrated elastic field, almost all of the elastic field is within the densification area. So you mainly measure densified material, not the material you want to measure. And this is the other way around for Berkowitz chip, which the main part of the elastic field is outside this densification area. So you get mainly the elastic properties of the material, the undensified material that you want to have. And this is also what you can see if you compare the elastic modulus determined from the cube corner tip to the elastic modulus of the Berkowitz tip over porosities. For high porosities, you get almost 2 times bigger elastic moduli if you use a cube corner, and this is because you only measure the densified material, which of course you don't want. So in principle for thin films, cube corner are better, but if you have porosity inside, densification, you have to go for the more challenging Berkowitz tip. Okay, that's it. I will give you a few take-home messages. If you don't get the whole thing, maybe you remember these 3 points. So for the determination of Young's modulus and hardness, a careful calibration and sample preparations is really necessary. And you have to take care for size effects and tip radii effects. Further developments, in situ testing, it's really a big thing these days. Determination of material parameters beyond Young's modulus, also very important, and very high-speed nano-indentation experiments. And on porous thin film testing, you have to take care of the densification. You can get an overestimation of the Young's modulus. With this, I want to thank you, yeah, I want to thank you from Dresden, Germany. This is how it looks like if the weather's good. And if you have any questions or so, you can contact me or the nano analysis cluster in Dresden. and I'm happy to answer your question. Let's see if we can manage it to answer questions. There are already some questions in the chat. I will go. Okay, now there's one question about the in situ SEM analysis, the drawbacks and advantages. Advantages, of course, you see what happens. You see, is there other cracks formatting? You see, is there plasticity? You see if there's pile up. And because in ex situ nano-indentation, you always have to assume that everything went well and everything is according to the theory you used. In situ, you see immediately what you're doing. This is the one positive thing. The next positive thing is you can use all the experiments that are accessible inside the SEM chamber. So you cannot only use the imaging, the SEM, you can also use, if you have a focused ion beam, so you can produce very small, complex geometries that you want to test, like bending beams, pillars, and so on, and you can produce more complex macromechanical experiments, and then using the indenter to conduct these experiments. And you have access in the chamber also if you mount it to EDX, so to chemical composition measurement, you can check around the area what chemical composition it has, or you have also EBSD, so crystallographic orientation. What we do a lot is in situ in the SEM, we put the sample there, we make an EBSD map, so we check the single grains which crystallographic orientation they have, and then we have the information, and then we make a mechanical experiment at one particular grain with the orientation that we want to have, and then we can have a look after the experiment and see if the grain rotating and what happens. So it's really, and this is almost impossible ex situ because you will never find the grain again. You'll only find it in situ in the SEM. These are all the advantages, and the drawbacks is that it's a little bit more time consuming. So you have to have the extra tool, of course. You have to mount it. The samples have to be a bit smaller. Sample preparation is a bit more demanding. But I think if you have complex tasks where you want to have like more information than just the hardness, then in situ it's a very good tool. So let me check. No more questions in the chat. Okay, there's another one. Very nice. To repeat the answer to the in situ SEM, or for the first question, let me check what was the first question. So the first question was about nanoparticles. Ah, okay. So nanoparticles, normally when we test nanoparticles, in situ, ex situ, in situ is much easier because you see when you hit the nanoparticle. Ex situ you have to guess a bit and then check from the mechanical data if you hit the particle or not. So nanoparticles, you normally use flat punch tip, so a tip that has a flat end, and then you have the particle on a substrate, and then you compress the particles between the two plates, so the flat punch and the substrate, and then you get a force displacement curve showing the compression of the particle. And then the first stage is you can get elastic deformation. If it's a hard material, then you can get determine from analytical solutions. You can determine the elastic parameters of the nanoparticles, and if you compress it more and you are in situ, you can see what happens. Either there is plasticity, you see slip lines and so on, or there is, I can go back to the, so this is a pillar, but you can also imagine this is a nanoparticle, and this is, you can see here the slip lines of the plasticity, or if you have a brittle nanoparticle, you can see fracture. And if you have then the mechanical force displacement data from the compression and you see the image, and you can normally with the tools we use, you can correlate the image to the mechanical data also in time. So you see if there's happened something in the mechanical data, this happened then to the particle or the pillar. And then you can see, okay, it was plasticity what was happening, or it was fracture it was happening. And then depending on the shape of the particle, if it's a ball-shaped particle, there are analytical solutions to calculate the stress strains at the moment of failure. Or if it's a non-spherical shape, you have to use finite element solutions to get the stress strain at the moment of fracture or plasticity, and then you can get information on the strength of the particles on the materials. And then you can also do it scale, so at different sizes of the particles, and normally you get the size effect if you have really nanoparticles where there are very few dislocations inside, or if you have big particles that behave different, so you can also check the size dependency of the behavior. But this is something you can do ex situ, but it's easier in situ because you then can have a better positioning and you see what happens to the particle if you compress it. Yeah, you're welcome. No more questions? Yeah, thanks a lot to you too. Okay. Bye.